In this lecture, we discuss reflection of a uniform plane wave from a conducting boundary. You will see that this will essentially make a foundation for a structure what is called a waveguide, which can guide electromagnetic waves along its length. So, in this lecture we still consider a media which is divided into two parts, on one side of which is a dielectric and other side of which is an ideal conductor. So, we talk here essentially the reflection from a conducting boundary. So, we divide the space into two parts, and in this case let me just draw the figure in a little different way. So, let us say the horizontal line is the one which is dividing the space into two parts, and I also orient the coordinate system a little differently, and the reason for that will become clear as we proceed in our discussion. So, let us say now the infinite medium is divided into two parts by this plane. Below this plane the conductivity of the medium is infinite, above this interface the conductivity is 0. So, on this side we are having an ideal dielectric, and below the interface we are having an ideal conductor. So, we have here a conductor, and on this side we have dielectric. So, we have here some permeability mu 1, permittivity epsilon 1, but sigma 1 is 0 for this, whereas in this case since we are having an ideal conductor, the sigma 2 is equal to infinity. So, this boundary then we can call as a dielectric conductor boundary, and the wave is incident on this boundary now from the dielectric side. The wave cannot come from the conducting side because your time varying fields will be 0 inside the conductors. So, there is no wave propagation inside the conductor. So, only wave can come from the dielectric side and get incident on this dielectric conductor interface. Let us choose now the coordinate system. Let us say this is my x axis. So, direction perpendicular to the plane of incidence and coming outwards is, let us say, that is y axis, and the direction along the interface now is z axis. So, the wave is incident on this at some angle. Let us say that angle is theta. I am not putting the suffix here because now we are dealing only with one angle, which is this angle. There is no angle in the second medium where the wave is not propagating in second medium because of infinite conductivity, and the angle of incidence and reflection is same, which we have already seen. So, this angle is also theta. So, this is a reflected wave. So, we have an incident wave and we have a reflected wave, and both these waves are going to make an angle theta with the normal to the interface, and that is what we had seen earlier. This condition is angle of incidence is equal to angle of reflection, which is the law of reflection. So, now we have an incident wave which is incident at an angle theta. So, the angle of incidence is theta and the angle of reflection also is theta, and there is no wave now in the second medium. So, there is no transmitted wave. We can consider again two polarizations, one is perpendicular polarization and one is parallel polarization, and do the analysis on the line identical to what we have done for a dielectric interface. However, this case is a rather simpler case because we do not have the three waves to match the boundary conditions, we have only two waves for matching the boundary conditions. So, in fact, this case is a simpler version of the case which we have already discussed. So, let us say we take a polarization which is perpendicular polarization. So, the E vector is oriented in y direction. So, let us say this is my incident field, and as we have done in dielectric case, again without losing generality, we can say that even reflected electric field has orientation in y direction. So, that is also perpendicularly polarized. Then by using Poynting vector, we can get the direction of the magnetic field. So, E cross H should give me the direction of the wave propagation. So, the magnetic field must be in this direction. So, this is H I, and since this wave is going in this direction, again E cross H should give me the Poynting vector. So, that should be the direction of the magnetic field H R. We can resolve the magnetic field into two components, one component which is parallel to the interface, other one which is perpendicular to the interface. So, if this angle is theta, this angle is also theta. Similarly, we can do for these two components. So, this angle is also theta. So, this component will be H I cos of theta, this will be H I sin of theta. Similarly, this will be H R sin of theta, and this will be H R cos of theta. So, in this case, the electric field is tangential to this boundary, because it is like this. So, when the wave is incident on this interface, which is this, the electric field is tangential to the interface. The component which is tangential to the interface for magnetic field is this H I cos theta. This is the component which is tangential to the interface. So, H I cos theta and H R cos theta will be the tangential components to the interface, and H I sin theta and H R sin theta are the normal component to the interface. Since we are having a conducting boundary now, we will have the surface currents. So, either I can use the boundary condition for the tangential component of magnetic fields with appropriate surface current, or if I want to be on safer side, I should always use the boundary condition which is always applicable without worrying about surface current, and that is the normal component of magnetic field. So, since there are no wave propagation or there are no fields in the conducting medium, the time varying fields, we do not have no fields in this region. So, that means my E t and H t are identically 0 in this medium. So, the boundary conditions now have to be satisfied only by these two waves, which is the incident and the reflected wave. But before we do that, let us now write down explicitly the expression for the incident and the reflected electric and magnetic fields, and then we will take the appropriate components of these fields and satisfy the boundary conditions. So, if I write the incident electric field is E I, that is having some amplitude E I, and we will have a phase function which is e to the power minus j beta. We are not using the term suffix 1 here, because since the wave propagation is going to be only in this medium and there is no wave propagation in medium 2, for simplicity let us say that the propagation constant beta in medium 1 is denoted by beta. So, without putting in a suffix 1, this is the phase constant of wave propagation in medium 1. So, here for this medium your beta is equal to omega square root mu 1 epsilon 1. Then we can write the expression here, this wave is travelling this way, this is direction x. So, the angle which the wave makes with the x axis is pi minus theta. So, you will get x cosine of pi minus theta, which is minus x cos of theta. The angle which this thing makes with the z axis is pi by 2 minus theta. So, that will give me plus z sin of theta, and the direction of this electric field is in y direction. So, let us put a unit vector for this, which is y. Same thing I can do for the magnetic field for two components. The phase function for the magnetic field for this will be similar to this, and for this one we can write. So, let us say first we write for the electric field for the reflected wave. So, let us say this is ER, that is some amplitude ER, e to the power minus j beta. Now, this wave, the angle which it makes with the x axis is not pi minus theta, but it is only theta. So, this quantity will be x cos of theta. So, that is x cos of theta plus the angle which this thing makes with the z axis is pi by 2 minus theta. So, that will remain z sin theta, and again we are assuming that this is oriented in positive y direction. So, we have unit vector y. So, we can write down, just once you know the angle of incidence, we can generate this phase function, and then we can write down the expression for the incident and the reflected electric fields. Same thing we can do for the magnetic field also. So, we have now the incident magnetic field H I, that is the H I is E I upon eta, and eta is the intrinsic impedance of this medium. So, we have in this medium eta, which is equal to square root of mu 1 epsilon 1, and we have a condition that E I upon H I is equal to eta, and same is true for this case also. So, E R upon H R are also equal to eta. So, we have from here E I upon H I, that is equal to eta, and same is true for this case also. So, that is also equal to E R upon H R. So, in medium 1, the ratio of electric and magnetic field for the incident wave is same as the intrinsic impedance, and same is true for the reflected wave, because both of them are the plane waves in medium 1. Once I get this, then I can write down here the vector magnetic field, and that we can have two components. One is the component which is along the x direction, which will be minus H I sin theta. So, this will be equal to minus H I sin theta. There is no y component of the magnetic field, so that component is 0, and then this component will be opposite to the z direction. So, it will be minus, this will be along x axis. So, this is unit vector x minus H I cos theta unit vector z, and both these fields will have a phase function which will be identical to this. So, this will be multiplied by e to the power minus j beta minus x cos theta plus z sin theta. We can write down the reflected magnetic field also. So, we have here H R, that is equal to, from here this is component is H R sin theta, but is opposite to the x direction. So, that is minus H R sin theta x direction but this component HR cos theta is in positive z direction. So, this is plus HR cos theta z direction with the phase function which is e to the power minus j beta, and the phase function for the reflected wave which is this function, so which is x cos theta plus z sin theta. Now, as we mentioned, this quantity EI and HI are related through the intrinsic impedance of this medium 1. So, we can write this HI in terms of EI. So, this thing expression can also be written as, I can take a minus sign common. So, this is minus EI upon eta. This will be sin theta x plus cos theta z, and this phase function e to the power minus j beta minus x cos theta plus z sin theta. And similar thing I can do for this also. So, I can substitute for HR which is ER upon eta. So, this thing is ER upon eta minus sin theta x plus cos theta z, and this phase function which is e to the power minus j beta x cos theta plus z sin theta. So, now I have got the expression for the electric and magnetic fields for the incident and the reflected waves. And now the problem is simple, just match the boundary conditions which are appropriate for this interface, and as we mentioned earlier, we satisfy the boundary condition which are always applicable, and that is the tangential component of electric field should be continuous and the normal component of magnetic field should be continuous across an interface. So, we take here now two boundary conditions. That is, the tangential component E tangential at the interface is continuous, and also the H normal is continuous. So, in this figure, as we have seen, the tangential component is the electric field is tangential to the interface. That means, sum of these two fields, if I put x equal to 0, that is the total field at the interface. So, the sum of the two electric fields at x equal to 0 should be equal to 0, because the field should be continuous and there is no field in second medium. So, sum of these two electric fields at x equal to 0 should be equal to 0. Similarly, sum of these two normal component of magnetic fields at x equal to 0 again should be 0, because the normal component should be continuous at the boundary. So, what we get from here, that if I just take EI and ER and put x equal to 0 in this, then we get E, which is EI plus ER Y e to the power minus j beta z sin theta, that should be equal to 0. This is for the tangential component of the electric field. So, this is the incident field which is y oriented, has a phase function, and at x equal to 0, this is the phase function. Same is true for the reflected field. So, this is the total field at x equal to 0, that is at the interface, that should be equal to 0. So, from here essentially we get a relation that EI is equal to minus ER. That is, the reflection coefficient in this case, which is ER upon EI, is equal to minus 1. In fact, the same condition I can get if I apply to the continuity of the normal component of the magnetic field. So, I do not have to really use this boundary condition, just by using the tangential component of electric field continuity, I can find out the reflection coefficient for the electric fields. So, in this case, the electric field reflection coefficient is always equal to minus 1. What that means is that initially we have taken direction of the electric field which was same as this, but now the reflection coefficient is negative. That means the direction of the electric field should be going inwards of the plane of the paper, and two amplitudes are equal. So, that means the reflected electric field is equal in amplitude with the incident field, but oriented in the opposite direction. So, sum of these two at the interface is 0. If you recall, when we were discussing transmission line, we had a reflection coefficient minus 1 for a short circuited load. That means the conducting boundary essentially is identical to the short circuit condition on transmission line. So, one side we are having a dielectric medium which is like a transmission line on which the wave is propagating. When it reaches to this ideal conducting boundary, the electric field is completely reflected from the boundary with a phase reversal, that means a phase difference of 180 degrees. So, this boundary essentially behaves like a short circuit in the transmission line terminology. Once we get that, then other analysis is very straightforward. You substitute now this value of electric fields into the expression for the electric and magnetic fields, and now ask what is the total field which will be existing in this medium, because there is nothing much to find out about the transmission and reflection coefficient. The reflection coefficient has become equal to minus 1, and there is no energy gone to the second medium. So, the finding out the reflection and transmission coefficient problem is a very simple problem in this case. However, what we would like to now study is that when this electric field is completely reflected, what kind of field pattern will be created in this medium, which will be superposition of these two waves. That is what is of interest now. So, let us say I take this electric field, and total electric field will be sum of these two electric fields at any point in medium 1. So, I can find out what is the total electric field which is sum of these two. So, with this condition, then we can get now the electric field in medium 1, which is, so E is equal to your EI plus ER, and now we are doing at any arbitrary point in space. I just take these two expressions, put ER equal to minus EI, and find the sum of these two fields. So, this will be equal to your EI this quantity e to the power minus j beta z sin theta is same for these two, only the sign of these is different. This will be plus j beta x cos theta this will be minus j x beta cos theta. So, these two are different for these two waves, but this quantity is identical for these two waves. So, I can take it common, get EI e to the power minus j beta z sin theta then for this wave what we have is e to the power plus j beta x cos theta. So, here e to the power j beta x cos theta, and for the reflected wave this will be minus j beta x cos theta, and ER is equal to minus EI. So, this will give me minus e to the power minus j beta x cos theta, and orientation of this is the y orientation. So, the total electric field which I have in medium 1, which is superposition of the incident and the reflected field, and ER is minus EI, we can write the total field like this. Now, this thing is we can combine. We know that e to the power jx minus e to the power minus jx is equal to 2 times j sin of x. So, we can use this to represent this as sine function. So, we get now the total electric field in medium 1, which is 2 times j EI sine of this quantity, which is beta x cos theta, with this e to the power minus j beta z sin theta, and that is oriented in y direction. So, we have now the electric field which has a sinusoidal variation in the x direction and is having a phase term which is only in z direction. What that means is that you are having an electric field now which is having a some kind of a standing wave behavior in the x direction, because this function it does not have phase, but it has an amplitude variation, and which can go from 0 to 1, which is the nature of a complete standing wave. So, this term now represents something like a standing wave which is in x direction, and a travelling wave which is given by this term which is in z direction. So, this term gives me a standing wave in x direction, and you get a travelling wave in z direction. So, the wave which you are going to have, which is a composite phenomena of the incident and the reflected wave, is a complex wave now, which is a combination of a standing wave in a direction perpendicular to the interface and a travelling wave which is in the direction of the interface. Same thing we can do for the magnetic fields also. So, we can take the two magnetic fields and get the expression for the magnetic fields also. So, when we combine these two, so we can get the x component, we can combine that, we can get z component, and we can combine that separately. So, we can get now the finally the expression for the magnetic fields also. So, we get here magnetic fields in medium 1 and let us take two components of the magnetic fields. So, I take x component. So, I get h of x, that is sum of these two components here. So, this will be minus E I upon eta sine of theta plus E R upon eta minus sine of theta. So, I will get from here minus E I upon eta sine of theta minus E R upon eta sine of theta, and the phase term for these two, this will be having plus j beta x cos theta, this term will be again common. So, you have to appropriately multiply this term by this phase term, which is e to the power j beta x cos theta. So, this has to be multiplied by e to the power j beta x cos theta, whereas this has to be multiplied by e to the power minus j beta x cos theta, and then the whole thing has to be multiplied by the travelling wave term, which is e to the power minus j beta z sin theta. So, this has to be then finally multiplied by e to the power minus j beta z sin theta. Again, if I substitute E r equal to minus E I, then I can get the expression, which is I can get this thing, this becomes plus E I. So, I can take minus E I upon eta common. So, that is minus E I upon eta sin theta, I can take common sine of theta multiplied by e to the power j beta x cos theta minus e to the power minus j beta x cos theta e to the power minus j beta z sin theta. Again, as we did in the previous case, we can combine these two terms using this. So, this will become 2 times j sin of x. So, this quantity will be minus 2 times j E I upon eta sin theta sine of beta x cos theta minus j beta z sin theta. So, the x component first of all has again similar behavior, that is, it has a standing wave component which is in x direction, and it has a travelling wave component which is in z direction. The same thing I can do for the other component, which is the z component of magnetic field, and I get here h of z, that is this quantity here minus E I upon eta cos theta, and this is E r upon eta cos theta, but E r is minus E I. So, essentially I get here minus E I upon eta cos of theta e to the power j beta x cos theta plus e to the power minus j beta x cos theta e to the power j beta z sin theta. Now I can again combine these two, that e to the power some jx plus e to the power minus jx is 2 times cos of x. So Hz can be written as minus ei upon eta cos theta, you can put 2 here, cos of beta x cos theta e to the power minus j beta z sin theta. So now we have got a complete description of the fields, that is, we got the electric field which is given by this, which is having a standing wave component and a travelling wave component. The x component of the magnetic field, it has a standing wave component and a travelling wave component, and the z component of the magnetic field, which has a standing wave component and a travelling wave component. So in general then we are having now the fields in medium 1 will be combination of travelling wave and a standing wave, and all of these fields are having a wave which is travelling in the z direction, positive z direction. That means it is travelling along the interface. So we are having a standing wave in a direction perpendicular to the interface, but all these fields are having a travelling wave which is along the interface, which is in z direction. Now we can make some observation from these 3 expressions which we got for the electric and magnetic fields. Firstly, if I plot the amplitude of the electric field as a function of x, when x is equal to 0, this quantity is 0, so the field is 0, and same thing happens even for the x component of the magnetic field. When x is equal to 0, the magnetic field will be 0. So whenever the electric field is 0, the x component of the magnetic field is also 0. In fact, the amplitude behavior of Hx and electric field, which is Ey, is identical as a function of x, and the magnetic field component Hz is a cos function. That means it is shifted by a quarter cycle in the x direction. So wherever Hx is 0, Hz is maximum, and wherever Hx is maximum, the Hz is 0. So if you plot this amplitude of the electric and magnetic fields, essentially we get as follows. So let us say this is my boundary, and I plot this. So let us say this is mod of electric field, which is Ey. The electric field behavior will be like that. Exactly identical behavior I will get for the x component of the magnetic field. So Hx also has same behavior. Whereas if I look at the magnetic field z component, that is shifted with respect to this, because this function is a cos function. So you have magnetic field z component that will be starting with maximum, it will go 0 here. So you will start from maximum, go 0 here, then and so on. So now we can make certain observations. This pattern, which is the standing wave pattern, which is created in x direction, this is x, x, x. The Ey and Hx patterns are aligned in space, whereas the Sz pattern is shifted by a quarter cycle with respect to these two patterns. So wherever Hx is maximum, the Sz is 0, and vice versa. This is the interface, which is the conducting interface, and since Sz, which is the tangential component, is not 0, essentially we will have the surface currents on the interface, and the magnitude of surface current will be equal to the tangential component of the magnetic field. So, now when the plane wave is incident on the conducting boundary, the surface currents are going to get induced on this surface, which is due to this tangential component of the magnetic field, as we have seen, and the normal component of the magnetic field will be 0, and the tangential component of electric field will be 0, as the boundary condition needs. Now, if we go back to the expression for the electric field, the electric field is 0 at this point, x equal to 0, but so it will be 0 whenever this quantity is multiples of pi. So, I have when this quantity is 0, the field is 0, and this quantity is pi, the field is again 0, when there is 2 pi, the field is again 0, and so on. So, if I go to this pattern here, these are the locations where this field is going to become 0. So, this electric field will become 0 for those values of x for which beta x cos of theta will be multiples of pi. So, we say that E y will be 0 when beta x cos of theta, that will be equal to multiples of pi. So, let us say this is m pi, where m is an integer, it could be 0, 1, 2, 3, and so on. So, now we have got this value of x, which is given by m pi divided by beta cos theta. And what is beta? Beta is the phase constant of the uniform plane wave in medium 1, which is nothing but 2 pi by lambda for uniform plane wave in medium 1. So, we can substitute, since beta is 2 pi divided by lambda, where lambda is the wavelength in medium 1, we get the value x will be m pi divided by 2 pi by lambda cos theta, that is to m lambda divided by 2 cos theta. So, at this distance x from the interface, if I go, the electric field will be 0, and that will depend upon, this distance will depend upon at what angle the wave is launched on the interface. So, if I consider a situation here and the wave is launched at this angle, I may find some distance here x at which the field will be 0, double of that again the field will be 0, and so on. So, essentially now we have got the planes which are parallel to this boundary, parallel to the conducting media interface, where the electric field will again be 0. So, in fact, you are going to have the multiple planes here in which the electric field will be identically 0. And since the electric field and the x component of the magnetic field have the same behavior, in those planes both these quantities will be 0. So, E y will be 0 and H x will be 0, and in those planes H z will be maximum. If I go by quarter cycle away, then you will see that the H z will be 0 and these two quantities will be maximum. So, essentially now we are defining some kind of a wavelength in the direction which is perpendicular to the interface, which is lambda upon cos theta, and multiples of this lambda upon cos theta, that effective wavelength, if I go lambda by 2 of that, at that location essentially the field will be 0. So, what we find that when the wave is reflected from a conducting boundary, we have created now the planes parallel to the conducting boundary where the electric field will be 0 in this situation, and the whole wave essentially is going to travel along the direction which is along the interface. We can get this electric and magnetic fields and ask a question now. One, of course, we know that the wave is traveling along the z direction, so there must be a power flow in the z direction, but we can also verify this from our Poynting vector argument, that if we calculate the average Poynting vector for this complex field which we have got, we must get the Poynting vector in the direction of the net power flow. So, since we are having the electric field which is y oriented and this quantity is 2 j E I, the magnetic field H x, if I take, if I look at these two expressions for E and H x, this quantity for electric field is 2 j E I and this thing is minus 2 j E I upon eta. So, if I calculate the cross product of E y and H x, it is in z direction. Since you are having both of them j, these two will be in phase with a negative sign. So, E y cross H x gives me a real value of the Poynting vector which is in z direction. So, I get E y cross H x which will be minus E z, and since there is a minus sign here, that gives me the net power flow which is in z direction due to this product. If I consider E y and H z component, you are having 2 j here for the electric field and this thing there is no j. That means the phase difference between the electric field and the z component of the magnetic field is 90 degrees. So, the cross product of E y and H z gives me only an imaginary term. So, the real part of the cross product of these two will be 0. So, E y and H z, which would give me the power in the x direction, that is purely imaginary power. So, there is no power flow in the x direction, but there is a net power flow in the z direction, because these two quantities E y and H x, these essentially gives me the Poynting vector which is in z direction. So, when we calculate the cross product of E and H, in this case we get average Poynting vector which is P, that is we have electric field which is, so we have here half real part of E cross H conjugate, and from here I get half real part of E y cross H, which has both the components. So, this is E y y cross H conjugate. So, that is half of real part of minus E y H x z direction plus E y H z conjugate x direction. And as we have seen, this quantity gives me a power flow which is purely imaginary. This is the quantity which is a real quantity. So, we get a power flow which is in the z direction. There is no net power flow in the x direction. And that makes sense that once you are having a boundary which is a conducting boundary, the power is not going to go inside this conducting boundary. So whatever power is incident essentially has to go back in medium 1. So this thing can be visualized as follows: the wave is incident which is in this direction, which is essentially having a component of propagation in this direction and something which is coming normal to the interface. The wave which is coming normal to the interface is completely reflected. So you get a standing wave which is created here. So whatever power flow was in this direction is completely balanced by the power flow which is in reverse direction, because there is a complete reflection. So the net power flow in this direction, which is in x direction, is 0. So this essentially gives you some kind of a reactive power in this direction, but in this direction where there is a net flow of the wave, you have a travelling wave in z direction and there is a net power flow along the z direction, and that is what precisely the Poynting vector gives you, that it gives you the Poynting vector in the z direction which is same as the net direction of the travelling wave, and there is no power flow in the direction perpendicular to the conducting boundary. What that means is that if you have a conducting boundary, then the boundary can be used to guide the energy along with it. So a conducting boundary has a capability of guiding the electromagnetic energy. So you launch a wave at any arbitrary angle, and what you will find is that the net power flow is always along the surface of this interface. Essentially this is the thing which is used in creating what is called a waveguide. So in a waveguiding structure we use the conducting boundaries so that the electromagnetic energy is guided along these boundaries. So now we will see when we discuss later that in those planes where the electric field was going 0, which was given by location of this, we have created now a structure that you have a boundary, then there are certain distances to these planes where again the electric field goes to 0, and if the electric field is 0 there, I can insert a conducting boundary there without affecting the field distribution. But by doing this, essentially I have created a structure which is bound from both the sides. At the moment I have a structure which is only bound from this side, but this side the space is open. But if I introduce another boundary here at a distance which is given by this, then the boundary condition will be satisfied at that boundary. Inherently fields will not get modified, but I would get a structure which will be a bound structure, and that structure will be what is called a parallel plane waveguide. So using the reflection from the conducting boundaries and the field expression which we have got here, essentially we have created a ground for developing a structure which is a structure like a parallel plane conducting geometry, within which the electromagnetic waves can be trapped, and we can have a net propagation of electromagnetic energy along these planes, along these interfaces. So with this understanding, now we are prepared to make a transition to a more realizable structure, what is called a parallel plane waveguide. So in next lecture when we meet, we essentially discuss the propagation of electromagnetic waves in a parallel plane waveguides, and again we will see some other characteristics of the parallel plane waveguide.